We've talked about how r and r squared measure how closely a set of points cluster around the line. It's not just how closely those points cluster around any line, it's how closely they cluster around what's called the best fit line or the least squares line, which is basically the single line that we think best represents the data. And so let's imagine that we had a set of points. I'm just going to draw the same 3 points for each one. Well, more or less. And so let's just imagine drawing 3 different lines. So let's say the first one that I draw is just like up here. And then I draw another one that's kind of like, oh, I don't know, maybe like that. And then I draw another one that's sort of going through it like, I don't know, maybe like that. And so what I want to do is I want to find which of these lines is really the best fit to our data. And so what I'm going to do is I'm just going to measure the distance between each dot and the line. So let's say that's like -5, it's like 5 points below. Let's say this is, call it -2. And let's say this is maybe a little bit more, maybe like -6 or something like that. And over here, this one's right on the line, so it's 0. This is a little bit above the line, so it's like 1. And this is a decent bit below the line, so maybe like -2. And over here, this is like maybe -0.5 below, 1 above, and 1 below. So what we're going to do is we're just going to say, okay, which of these green lines is closest to the different dots that we have? And the way that we find that is that we're going to take each distance from the line and square it to make it positive, because if it's above or below, we don't care. We just want to know sort of the absolute value of the distance from it. So -5 squared plus -2 squared, I'm just going to add up these. These are called the residuals. So 25 plus 4 plus 36. And this one, 0 squared plus 1 squared plus -2 squared. And this one, -0.5 squared plus 1 squared plus -1 squared. This would be considered our best fit line. And it would be that because the sum of the squared errors, or the sum of the squared residuals, the sum of the squared distances from each point to the line, is the smallest. So the reason that we want to find these is because the line tells us some useful information about the two variables that we're thinking about. So interpreting the best fit line. So let's say that we have a best fit line that's going through some data. And this was kind of the best we could do. That best fit line has a y-intercept. And what this y-intercept tells us is it tells us the amount of y when x is 0. And we also have a slope. Here, I'll extend that line a little bit further. How much additional y we get for each additional x. So let's do a couple of examples. If x represents number of TV ads, oops, that should just have one D. A car dealership airs per week, and y is the number of people entering per week, and the best fit line is y hat equals 4 plus 1.5x. And this y hat, it just has a hat on it because it's a predicted number, not an exact number. Interpret the y-intercept, interpret the slope. It's a convention that oftentimes these lines get written with the y-intercept first and then the x term afterward. Same thing if you go the other way, but we'll just follow convention here. So the y-intercept means when x is 0, what's y? So if there were no ads, 4 people would enter. The slope means that for each additional ad, 1.5 more people enter. And this is on average. Obviously, you're not going to have half a person walk in the door, but the general idea is that our best prediction for how many more people would be about 1.5. Obviously, we can see from the graph there's some variation around that. So let's look at a couple more interpretations. X represents number of firefighters. In Oakland, and Y represents dollars of fire damage. Per year. Y hat is 1 million minus 10,000 x. I'm just making up these numbers, but anyway, we'll work with this. So let's interpret the y-intercept and the slope. So the y-intercept means that if there were no firefighters, if x were 0, there would be $1 million in damages. And the slope means for each additional firefighter, there are $10,000 less, because notice this is negative, we're subtracting $10,000 for each additional firefighter. In damages per year. So that's how those work generally. However, notice that sometimes something like this will happen. X is the number of lunches thrown in the room trash can, not outside. And Y is the number of ants in the room after lunch. If Y hat equals -2 plus 12x, interpret the y-intercept, interpret the slope. So notice if we just go with how we were doing it, we would say the y-intercept here, if there were no lunches, there would be -2 ants. This doesn't make sense. Basically what's going on here is that what we have data for is our values that aren't necessarily all that close to 0 for x. And so there might be a linear relationship between the two variables later on, but there might not quite be a linear relationship near 0. So maybe, for example, there's something that looks like this. Right near 0, there's a bit like that. It sort of curves up a little bit, and then we start sort of seeing this linear relationship here. So in that case, when I draw my best fit line, it might very well be very nicely fit right here, but not quite so well fit near 0. So we end up with that negative y-intercept right there. So this works mathematically. But not in the real world. It doesn't make sense in the real world terms. It's just sort of what we need to have in order to get the equation to line up right over here. So this is not uncommon that our y-intercept just doesn't make sense in the real world. That doesn't mean it's wrong. It just means that we're not going to use that right near 0. We're just going to use it for ones where it's a better fit. And our slope is going to be just like normal. Each additional lunch, I won't say leads to, because that would imply that it causes it. We don't know that. That's just correlation. Is associated with 12 more